Hello everyone, my name is Alvaro, and in this video I will be covering another problem in the blind Leetcode 75 problem list. Today the problem is merge two sorted lists, which is problem 21. As usual, I will put the link of the problem in the description, and this problem involves using linked lists. So let's take a look at the code and the problem statement and let's get to it. So the problem statement says, you are given the head of two sorted linked lists, list 1 and list 2. Merge the two lists in one sorted list. The list should be made by splicing together the nodes of the first two lists. Return the head of the merged linked list. So example 1, we have list 1 here, and then list 2 on purple. So what we return is just a sorted list here. So we return a 1, and then a 1, then a 2, then the 3, and then a 4, and then the other 4. So the output looks like this. If both of them are empty, then we just return empty, which is understandable. And if one of them is empty and the other one is not empty, then we return the other one. So that's pretty straightforward. So let's see, one of the linked list nodes has, well, each linked list node has a value variable, and then it has a next variable, which is a pointer towards the next one, which is represented by the arrow in the diagram. So for example, this node dot next is equal to this node. And we are given list 1 and list 2, which are the heads of the list, since they are of type list node. All right, so let's think of the approach right here. If you want to work by yourself, just pause the video, take a little bit of time, and then proceed to continue if you're lost or you want to compare code. So the approach that we are going to use here is that we are going to create one variable that will represent the head of the list that we want to return, and we will use two pointers. One pointer towards the head of list 1 that is in the beginning in the head of list 1, and another pointer that in the beginning is in the head of list 2. And what we are going to do is we are going to compare the nodes that each of the pointers points to, compare the values, and whichever one is smaller, we just append to the list that we want to return. In the case that the values are equal, it seems that there is no preference on which one we should append, as you can see in the diagram. For example, here, the purple goes first over the red node, but in this case, the red node goes over the purple one. So it seems that there's really no difference. For the sake of just uniformity, what I'm going to do is I'm going to pick the node in list 1, but again, you can do list 2 in the case that there's a tie. It really does not matter, but you have to make sure that you take care of that case. So what we are going to do is just compare the pointers and just keep appending them. And at some point, we are going to run out of space in the list. So for example, if we just keep adding and adding and adding, at one point, one of our pointers is going to reach null because we've appended every single element in the list. And at that point, there's only going to be one pointer that is not null. And at that point, we just simply append whatever's left of that pointer to the resulting list. So let me explain by using the example. In the beginning, we add the 1s, then the 2, then the 3. And at this point, both pointers point towards the 4 in each list. So here we just add node number 4. And once we add node number 4, we move to the next element. And when we notice that this element points towards a null element, there is no reason to start comparing a null element with a node. We know that whatever we're going to add to the list is whatever is remaining in list 2. Therefore, we will simply append whatever is remaining of the non-null pointer to the resulting list that we want to return. And that'll be it. So let's get to code. So let's start by creating, what we're going to do, I think it'll be easier for us if we start with a pointer towards the head. So pointer 1 is equal to list 1, to the head of each list. Pointer 2 is equal to list 2. And now both pointers point towards the head. I think it'll be easier just to write less lines if we create a dummy node, here. We can just say something like dummy head. I think it'll be easier to know what we're doing if we name it this way. So we can just create the variable here. Default value is 0, so I don't even need to define that, so that's nice. And then what we can do is, while both pointers are not none, and this is equivalent to saying while pointer 1 and pointer 2, so these like not equals none statements are not really necessary, but I prefer to write them for the video for the sake of clarity. If you want to just read the code later and try to understand how it works without watching the entire video. So while pointer 1 and pointer 2 are not none, we compare the nodes that each node points to. So if pointer 1 dot val is less than or equal to pointer 2 dot val, and like I said before, the equals case does not really matter which one you choose. Just make sure that you handle the case properly. In this case, what we can do, and I forgot to create a node that we will use to loop through the list that we want to return, we can say that current.next is equal to pointer 1, and then we move the pointer 1 towards the next element in list 1. The other case is when pointer 2 val is greater than pointer 1. So if you chose to do this, then the other case would be when pointer 2 val is greater than or equal to, in which case, in the case of a tie, you would append the purple one, and as you can see in the diagram. It really does not matter. So if this is the case, what we can do is current.next, we append the element in list 2, and then we move the pointer in list 2. And after we're done with that, now we just simply move the pointer of the list that we want to return to keep adding nodes towards the end of the list. And this is how we loop through both of these lists and the list that we want to return. And like I mentioned before, at the end, one of the pointers will be none, in which case what we will do is simply append the pointer that is not none. So if pointer.1 is not equal to none, then current.next is equal to pointer 1. And if pointer 2 is not equal to none, then current.next is equal to pointer 2. And at the end, like I mentioned before, the dummy head is just a node with a value that does not exist in the list, but the value right after it is one of the nodes that exists. Therefore, we will return dummyhead.next. The reason why I chose to use dummy head is because if I didn't use that, it would take a couple more if statements. It really does not matter on the efficiency of the program, but I would need to create a variable. We can say like head, for example, set it equal to none, and then say, okay, if pointer 1.val is less than or equal to pointer 2.val, then the head is this, and then I set pointer 1 equal to this, and in the other case, I set head equal to this, and I move the pointer here. And I rather just create an extra node so that I don't have to write extra if statements, since these ones take care of everything properly. So now we run the code and then submit it. And as you can see, faster than 91.4. Like I said multiple times, don't really guide yourself too much on whether this is faster than 87% or 70% or 90 whatever percent of the solutions, since it varies a lot with the connection makes this vary a lot, and also just compilation and runtimes aren't consistent. But yes, this solution is the most efficient. The runtime of this solution will be big O of the minimum between, actually no, it will be big O of n plus m, where n is the length of one list and m is the length of the other list. The worst case scenario is we just traverse every single node on each list except one, because there will always be the last one, just hanging in there. But yes, the runtime will be that. And the space-time complexity, since the space-time complexity should be big O of 1, since we're not creating any other elements. But if you want to count the edges of each node in the list, then the space-time complexity is big O of n plus m. However, I would argue that the space-time complexity is big O of 1 because we're really just creating one extra element in memory, and we're simply adding edges. Alrighty, so that's the end of the video. I hope you enjoyed it and you found it useful. And see you in the next one. Thank you very much for watching. Bye-bye.